Hi, it's Nova again, and I'll be your guide today as we explore the night sky. Along with the assigned readings, in this presentation we'll explore the ideas of winter and summer solstices, the orbits of the planets, the origins of the concepts of months and days, and dimensional sizes of our local objects. The learning objectives are to continue to understand the scope of astronomy and start to gain an ability to describe the cosmos. This includes its physical dimensions, properties, and components. Historically, constellations were imaginary configurations of stars named after a person, object, or animal. Today, constellations are defined into 88 contiguous regions that cover the entire celestial sphere and all the objects in that region. In the next slide, we'll hear what Professor Quasar has to say about the Orion the Hunter constellation.
The Orion Hunter constellation was originally only a group of 10 stars, Betelgeuse, Rigel, and several others. Today, Orion is an entire region of space, shaped like a goofy Nebraska state, which extends as far out as we can electromagnetically detect objects, which currently is at a distance of 13.7 billion light years.
These are images of the constellations of Orion the Hunter, Sagittarius, and Scorpius. Betelgeuse is 640 light-years from Earth. Bellatrix is 500 light-years from Earth. Mintaka is 915 light-years from Earth. Its size is approximately 20 times the mass of our Sun. It is also 20,000 times brighter than our Sun, with a surface temperature of about 60,000 degrees Fahrenheit. That's 10 times hotter than the surface of our Sun. Rigel is 900 light-years from Earth. Saiph is 650 light-years from Earth. Alnitak is 1,600 light-years from Earth. It contains the famous Horsehead Nebula. The Great Nebula of Orion, M42, is 24 light-years wide at a distance of over 1,300 light-years from Earth.
Nebulas are the stellar nursery regions of space, not stars.
Take a good look at this image. Can you spot the Orion constellation? The celestial sphere is an imaginary sphere of very large radius that contains the night sky. The celestial poles are imaginary points around which the celestial sphere appears to rotate. The celestial equator is an imaginary great circle on the celestial sphere. It is 90 degrees from the celestial poles. Declination is the coordinate on the celestial sphere analogous to latitude on Earth. It is measured north and south of the celestial equator. Right ascension is the celestial coordinate analogous to longitude on Earth measured around the celestial equator. The measurement of right ascension begins with the start of the vernal equinox, which is around March 21st each year.
Okay, now look, relax. Let's not get all excited about right ascension and March 21st and spinning, and just understand that like on Earth we have longitude and latitude. We invented a system for measuring a coordinate system in the sky called declination and right ascension. Since we already use longitude and latitude on Earth, we needed two new terms. So just remember, declination is equal to latitude on Earth, and that would mean that right ascension is what? Longitude. Very good. Now we can move on. Thank you.
The equinoxes are the 2 times per year the sun crosses the imaginary celestial equator. This means that everywhere on Earth, day and night are of equal length. The vernal equinox occurs around March 21st. The autumnal equinox occurs around September 23rd when the sun crosses the celestial equator, moving from north to south. The ecliptic is the name of the apparent annual path of the sun on the imaginary celestial sphere. Ecliptic is inclined to the imaginary celestial equator by 23.5 degrees. This is because of the actual 23.5 degree tilt of the Earth's axis of rotation relative to the plane of the sun. The northernmost point on the ecliptic is called the summer solstice. The southernmost point on the ecliptic is called the winter solstice. Review the following images and then proceed to the next slide.
The ecliptic is the path of the sun. It has 4 major points: the summer solstice, the winter solstice, and the equinoxes, spring and fall, which are of equal length.
Now let's talk a little about the Earth. The Earth's rotation creates the day-night cycle. The rate at which Earth rotates determines the length of the day. So 24 hours equals 1 day, which equals 1 rotation on our axis. Moreover, this instantly tells us the speed of the Earth's rotation on its axis. Now let's talk a little about the Earth. So let's calculate the Earth's rotational speed. If we were to do the math, it shows that r is equal to the Earth's circumference, which is 24,901 miles, divided by 24 hours. This equals 1,038 miles per hour. So the rotational speed of the Earth on its axis is 1,038 miles per hour. Seasons are caused by the 23.5 degree tilt of the Earth's axis of rotation. Earth's orbital revolution around the sun defines the length of the year. 365 days equals 1 revolution. Hence, our definition of time is the period it takes for the Earth to return to its position relative to the background stars seen on the previous turn of the imaginary celestial sphere. Phases of the moon originally inspired the concept of the month. The names of the days of the week are derived from astronomy and mythology. Saturday. This day is named after the Norse god Saturn. Sunday. This is Germanic and means day of the sun. Monday. This is Germanic and means day of the moon. Tuesday. This is from Tri, the Norse god of war. Wednesday. This is from Odin, the Norse god. Thursday. This is from the Norse god Thor. And Friday. This is from Frigg, the Norse goddess of love. To measure something means to compare it with a standard quantity of the same kind called a unit. The system of units used by science is called the SI system. The SI unit of length is the meter. So what does a meter equal? 1 meter is equal to 100 centimeters. 1 kilometer is equal to 1,000 meters, or 10 to the 3rd power. 1 gigameter is equal to 1 billion meters, or 10 to the 9th power. When we go smaller, we see that 1 nanometer is equal to 1 billionth of a meter, or 10 to the negative 9 power. Wavelengths of light are measured in nanometers. The SI unit of time is the second. The SI unit of mass is the kilogram. And the SI unit of energy is the joule.
Let us never speak of the metric system again. I need miles and hours to understand. For you European metric fans, you'll just have to muddle through with English units. Sorry about that.
The average distance between the Earth and Sun is 93 million miles. This unit of length is called the astronomical unit. Remember that we learned in the first module that 1 AU is equal to 93 million miles. As a unit of length, its primary application is for measuring distances within our solar system. Jupiter, for example, is an average of 5.2 times farther from the Sun than the Earth. Thus, the average distance between the Sun and Jupiter can conveniently be stated as 5.2 astronomical units. So let's see why astronomers love their AU symbol. Jupiter, on average, is 483 million miles from our Sun. Which one would you rather type all day? 483 million miles or 5.2 AU? The average distance from Pluto to our Sun is approximately 3.647 billion miles. Nope. To astronomers, Pluto is just 40 AU from our Sun, and we are 1 AU. The speed of light measures distance. Speed of light is 186,000 miles per second. In 1 year, a beam of light travels 6 trillion miles. The symbol for the speed of light in empty space is called c, so that the speed of light is equal to c, which is equal to 186,000 miles per second. The symbol for the light year is ly, which is the distance light travels in empty space in 1 year. 1 ly is equal to 6 trillion miles, which is equal to 63,000 AU. For larger distances, kilolight years and megalight years are used. The ancients were unable to tell the distance to any object in the heavens. Thus, they invented a system of angle measuring to denote relative positions at apparent sizes of objects in the sky. This angle measuring system is still used today. To locate stars on the celestial sphere, for example, we do not need to know their distances from Earth. All we need to know is the angle between one star to another in the sky. This is a property that remains fixed over our lifetimes because the stars are all so far away.
Okay, now take a breath again. Think, calm down. You all met a protractor and a pencil somewhere in your academic career. Like, say, grade school. Just think for a second. If you know what a 90-degree angle is, or what a 45-degree angle is, well, then you already know what angles are and angle measures are. So I really didn't teach you anything new. So this next bit of information won't come as a shock to you. If you don't understand that two objects in space can be separated by a 5-degree or a 1-degree angle, well, then you are in for a shock. But otherwise, you'll follow along.
An arc angle is the opening between two lines that meet at a point. Angular measure is a method of describing the size of an angle in units of degrees. On the sky, we measure distances between objects as angles. Because of the vast distances involved in the cosmos and the invention of the telescope, we are able to detect smaller and smaller angles between stars beyond observation with the naked eye. Angles smaller than 1 degree are broken down into a special pair of units called the arc minute and the arc second. The full circle has 360 degrees. 1 degree has 60 arc minutes, and 1 arc minute has 60 arc seconds. Thus, an arc second is a measure of a very tiny angle between two objects. We also have the parsec. The parsec is defined as the distance at which two objects separated in space by 1 astronomical unit make an angle of 1 arc second. This works out to be a distance of 3.26 light years. So how were we able to determine distances to objects in the heavens? It was not until 1838 that German astrophysicist Friedrich Wilhelm Bessel invented a method to measure the actual physical distance to a star. This effect, known as parallax, is the most straightforward way of measuring stellar distances. This is the apparent displacement of an object because of a change in the observer's point of view. To measure distance to a star, astronomers measure the parallax shift of the star using 2 points of view that are as far apart as possible, at opposite sides of the Earth's orbit. The direction from Earth to a nearby star changes as our planet orbits our sun, and the nearby star appears to move back and forth against the background of more distant stars. This motion is called stellar parallax. The parallax of a star is equal to half the angle through which the star's apparent position shifts as the Earth moves from one side of its orbit to the other. Instead of using light years, it is simpler to measure the distance in parsecs. So a star with a parallax angle of 1 arcsecond is at a distance of 1 parsec. If the angle parallax is measured in arcseconds, then the distance to the star in parsecs is given by following this simple equation. D is equal to 1 divided by P, where D is equal to distance to a star in parsecs, and P is equal to the parallax angle of that star. This is the relationship between a star's distance and its parallax. This simple relationship between parallax and distance in parsecs is one of the reasons astronomers usually measure cosmic distances in parsecs rather than light years, because it yields simple algebra equations.
Whoa, Nova, slow down. You're getting all technical and numbery on us. Is this on the exam? It's like some kind of weird, world stuff you're into here. Is this really fair? Okay. So the Pythagorean theorem says that if I know the length of 2 sides, I can calculate the length of the third side, C. But Bessel also knew trigonometry, a fancy kind of triangle measurement that says if you know the angle between 2 sides, you can calculate the length of the third leg, the distance D in the equation D equals 1 over P.
Come on, Professor Quasar, it's astronomy. Of course it's going to get a little technical here and there. Barnard's star, for example, has a parallax of 0.545 arcseconds. Hence, the distance to the star is straightforward. D is equal to 1 over P, which is equal to 1 divided by 0.545, which equals 1.83 parsecs. There is, of course, an equation that converts parsec distance to light-year distance. 1 parsec is equal to 3.26 light-years. To express the distance to Barnard's star in light-years, D is equal to 1.83 parsecs times 3.26 light-years, which equals 5.98 light-years. Proxima Centauri has a parallax of 0.772 arcseconds. Since D is equal to 1 over P, its distance is 1 divided by 0.772, which equals 1.3 parsecs. And 1.3 parsecs multiplied by 3.26 light years divided by 1 parsec equals 4.24 light years. We learned earlier that 1 light year is equivalent to 6 trillion miles. So when we do the math and multiply 4.24 times 6 trillion, we get 25 trillion. Therefore, our next nearest star neighbor, Proxima Centauri, is 25 trillion miles away. Review the following images closely. Here you can see the measurement of a stellar parallax for 2 stars at different distances. This shows the change of parallax angle with distance. This is humanity's first method of measuring the actual distances to stars, and it did not arrive until 1838 and the work of Friedrich Wilhelm Bessel. This trigonometry parallax method works for stars up to a distance of 500 light-years. For measuring distances of objects beyond 500 light-years, astronomers have invented very sophisticated methodologies that are beyond the scope of our course.